Gas law, PV equals nRT. The ideal gas law uses variables of the gas laws, temperature T, pressure P, and volume V, along with the amount of the gas, which we will measure in moles and will be represented by a lowercase n. So therefore our values for these problems, we will look for n, the number of moles of gas. We will use R, which is the gas law constant, 0.0821 atmospheres times liters divided by moles times Kelvin. This constant is a value you need to remember, and maybe you should write it on your periodic table. Pressure, P, is measured in atmospheres. It must be in ATMs to match the gas law constant. Volume must always be converted to liters, again to match the gas law constant. And as with all gas law problems, we must convert Celsius to Kelvin. Sometimes in these problems you will be given the amount of gas in grams and will need to convert it to moles by stoichiometry, stoichiometric conversions. In this sample problem, a 5-gram sample of methane gas, CH4, is held in a 2.5 liter chamber. The gas inside the chamber is at 25 degrees Celsius. What is the pressure of the methane gas? The first thing we need to identify is that we have a 5-gram sample of methane. Knowing that we have a 5-gram sample, we know we must convert to moles of methane. Carbon has a mass of 12 from the periodic table. There's 1 carbon atom in methane, so 1 times 12 equals 12. There are 4 atoms of hydrogen in methane, so 4 times the mass from the periodic table, which is 1, equals 4. And 12 plus 4 equals 16 grams of methane. Doing the stoichiometric conversion, 5 grams of methane times 1 mole of methane over 16 grams of methane, we get a value of 0.3125 moles of methane. This will be our n value. We next look for the other values that we need to work with. 2.5 liters is our volume, and 25 degrees Celsius is our temperature. We must convert the 25 degrees Celsius to Kelvin, so we add 273 to get the 298 Kelvin value. We are looking for what is the pressure of the gas. So therefore P is our unknown. We can now work the gas law, the ideal gas law equation. PV equals nRT, where P is the value we're looking for. The volume is 2.5 liters. The number of moles is 0.3125 moles. The gas law constant, which is always the same, 0.0821 atmospheres times liters divided by moles Kelvin, and our temperature is 298 Kelvin. Completing the algebra, we get P equals 0.3125 moles times 0.0821 times 298 Kelvin divided by the 2.5 liters. When we do this in the calculator, we get an answer of pressure at 3.06 atm. Let's look at another sample problem. Oxygen gas is held at 1200 milliliters in a tank at 30 degrees Celsius and 900 torr. What is the mass of this gas? First, convert all values to proper units for the ideal gas law constant. Therefore, we need atmospheres, Kelvin, and liters. 1200 milliliters, we move the decimal 3 to the left and get 1.2 liters. 30 degrees Celsius, we add 273 to get 303 Kelvin. And we convert 900 torr to atmospheres by multiplying by 1 atmosphere over 760 torr for a 1.18 atmosphere value. So therefore our pressure was 1.18 atmospheres. Our volume is 1.2 liters. Our mole value is what we're looking for in this case. R is always the same, 0.0821 atmospheres times liters divided by moles Kelvin, and our temperature is 303 Kelvin. We can plug these values into the ideal gas law equation, which is PV equals nRT. 1.18 atmospheres times 1.2 liters equals the number of moles, which is what we're looking for, times the ideal gas law constant times 298. When we do the algebra for this one, we end up with 1.18 atmospheres times 1.2 liters divided by the gas law constant times 298 Kelvin. Notice how atmospheres cancel, liters cancel, and kelvins cancel, leaving us with moles. When we do this on our calculator, there are two ways we can do this. 1.18 times 1.2 divided by 0.0821 divided by 298, or 1.18 times 1.2 divided by parentheses 0.0821 times 298 close parentheses, and either way we will get 0.058 moles of oxygen. Unfortunately, this is not our answer, as we are being asked to find what mass do we have of the gas. And therefore we must do the stoichiometry next by taking that 0.58 moles and we must convert it to grams. 0.058 moles of O2. We are reminded that oxygen in its gas form is always O2 because it is diatomic. Therefore, the 16 from the periodic table has to be multiplied by 2 atoms to get 32 grams of oxygen for the molar mass of oxygen. 0.058 times 32 grams divided by 1 mole gives us a final value of 1.86 moles of oxygen for this answer.